So let's continue with linear regression. So in linear regression we use a very similar neuron, if you want, as in the perceptron, and in fact this is sometimes called ADLINE, adaptive linear element. But it's also well known in statistics and many other fields. The difference is that we calculate the h of x as before, but now the h of x is the output of the neuron. So the target function or the target values can assume any real value, and we don't force the neuron to make a decision, 1 or -1 or 1 and 0. We say make a prediction. Let's directly look at the cost function. So if we have a linear function f of w of x, then we sum over all data points. So I iterates from 1 to n. And we look at the difference between the prediction, so f of w of xi would be the prediction, and the target value in training, yi. We take the difference and then we square it. So it's called squared loss function or least squared error cost function. And the solution to this problem, the minimizer of this cost function, is the function or the parameter setting which minimizes this term, the cost function. And it can be, it doesn't always have to be unique, but later we will make it unique. So for visualization, we assume that there's only one input, although linear regression works really best in high dimensions. So here's the input x, and here's the output y, and here we see data points. So in this case, we can easily visualize the data points. Here are these dots, and what we are getting is this equation here, or this formula here. It's a linear function because it's a linear system. And in this case, the function increases linearly when we increase x, and the place where this line would hit x equals 0. So this the y level here would be the w0. So in one dimension, it's just w0 plus w1 times x. The weight vector only consists of w0 and w1. The squared error doesn't change, and we're looking for the minimum. So you might have done this in high school or during your studies. In German it's called Ausgleichsgrade. So we can write this also in matrix vector form. Here's the function w0 plus sum over all inputs, so the real inputs, from 1 to m, the inputs which vary with each data point, multiplied by wj. And we can write it in this compact form as an inner product. When we define w to be w0, w1 to wm, and xi from 1 to x, the first input to the mth input. You remember from last lecture that the inner product is simply the sum over the components. So this is just a very convenient way of writing this sum here. In 2 dimensions, it would look like this. So you have this linear plane, and the data points would be maybe not on the plane, but hopefully near the plane. Also an important point is, of course, the prediction will not go through all the data points. It might go through these 3 ones, but not to all of them. But this linear function, of course, would be our prediction for a new data point. So if we get a new data point here, let's say x equals 1, then we would predict this. So we can generalize to new inputs. And if we look at the contribution of one data point to the cost function, so if the prediction varies from the target, so this is indicated here, every data point makes a contribution which is a square to the distance from this data point. So if you only would have this data point, of course, we would predict this. The prediction would exactly be this yi in the training data, but otherwise we would be a little bit off. And we can also elegantly write the prediction as in a matrix vector form. So remember, the matrix X has in its rows all the data points represented, and we multiply it by a W, or by our estimate of W, and then we would get the prediction for all the data points in the training set. So we can apply gradient descent and stochastic gradient descent as we discussed before for the perceptron. So we have our cost function, and we take the gradient, we calculate the gradient with respect to Wj. So the sum remains the sum. This is a quadratic expression, so this is 2 times the inner term, so 2 times the inner term, and then the inner derivative. So we're applying the chain rule. If we take the derivative of this term with respect to Wj, we're only left with the xij. So we get the difference times the xij. So if we are interested in Wj, it's the jth input of the ith data point. And as before, we want to go in the negative direction of the gradient. So a sensible learning rule would be for all j. Wj is the old Wj plus eta. Eta is the learning rule again, times the sum of all data points times xij. And when we take the stochastic gradient descent version of this learning rule, we obtain the Adeline learning rule. Adeline stands for adaptive linear element, so that uses stochastic gradient descent. So let x of t and y of t be the training pattern in iteration t, maybe randomly chosen. Then we adapt. So the new Wj is the old Wj times plus eta, the true target minus the prediction times x t of j, and we iterate over all w's. Yeah, interestingly, this formally looks like the perceptron learning rule. In the appendix, I showed you that the perceptron learning rule can be written in this form, but for the perceptron, the target can only be -1 and 1. And of course, the prediction would also be only -1 and 1. In the Adeline, y of t and y hat of t can assume any scalar number. But also now you see something which looks like Hebb's rule in some sense, also generated a lot of excitement, was sort of invented around the time when the perception learning rule was invented. So the adder line is optimized by stochastic gradient descent. And so I use this index t also because it can be time. So sometimes data points arrive sequentially. It's sort of in single processing applications. And then you can just absorb new data, and your parameters in your system can also adapt to the changes. Because this learning rule only goes sort of forward in time in this case. So you can generate a online learning system, and in fact the adder line is one of the standard methods if you're interested in adaptive single processing. With a fixed training data set, so we don't do this online adaptation now, the least squares solution can be calculated analytically in one step. This is then also called least squares regression. So again, let's look at the cost function, and now we look at this design matrix again. So here I've written it again, and y is the vector of targets. Then we can write this cost function. Now it's a sum over terms, so we can write it as some form of an inner product. And the vectors in this inner product are the difference between the target values, or the target vector, and the vector which is the vector of the predictions. No? So remember I said W hat, so our prediction is this design matrix X times W. So this is the vector of the differences between the prediction and the targets. We take transpose, so we make out of the row vector column vector, and we multiply it with the same vector. So this gives us the summation. This difference gives us the difference. So we can write the cost function in this convenient way, without any sums or indices. And you might remember from high school or from wherever that a necessary condition for an optimum is that the first derivative is 0. It's not sufficient, but it turns out in our case it's also sufficient. So I want to bring you a little bit closer the equations which we will get. And I start very simple with just one input and no constant. So W naught would be 0. Then our function is just x1, w1, and the cost is just the sum over all data points, yi minus xi1 times w1. And you should remember from high school days that you can apply the chain rule for this. So you take the derivative with respect to w1. Again, you get 2 times this term, the sum remains, and then the inner derivative is written here, and the inner derivative of course is xi1. So we get this term, then we multiply out these terms, and we get this expression over here. And this expression over here, and the w1 is now, so it's just a number, and this is also just a number. So to get, so I just divide, I will set this to 0. Now we want to set the derivative to 0, and calculate the w1, which is just, so this goes to the other direction, then the sign changes to plus, and we divide this term by this term, and this is what I've written here. So this is this term. So this is just a number, and this is also just a number. So I divide 2 numbers and get my least squares estimate for w1. So now we're doing exactly the same thing, only that we use our nice vector notation. So x1 bar is now the vector of all, so the input for all data points, so from 1 to n. And the cost function can now be written in this form. The difference between prediction and targets multiplied by itself. So this is a vector now, and here we take the transpose to get the sum. So we have to take the derivative of this expression with respect to w1, and we get, essentially, you have to, I will show you the equations later which we are using, but it's so it's more or less always the way how you take the derivatives with respect to scalars. You just have to pay attention where you put the transposed, and I will show you the rules in a second. So we get 2 times this expression, and then the derivative of this difference of vectors with respect to the w's, and this becomes this expression, the difference vector multiplied by x1 transposed. So this, remember, this was the vector of all inputs. We can multiply it in these 2 terms. Fortunately, these are still scalars, so we can write the same thing as we written here in this maybe more convenient form. So this is the this is exactly this sum of the components here of the inputs times the outputs, and this is just a short form for this expression over here. So now that we know how to do this in vector format, we are ready to take on the complete problem. We defined before that we can write the cost function in general as the vector y minus x. So x is a design matrix times w transposed, and times the same vector without the transpose. So this gives you the inner product. And then we take the derivative, which we want to set to 0. So this is sort of a quadratic form. So we get 2 times this term out as before. And then we have to calculate the derivative of this difference of these 2 vectors with respect to w. And the solution is minus 2 x transposed times y minus xw. So this is like what this term becomes. And we can write this again into 2 terms. So minus 2x transposed y plus 2x transposed xw. So we get this product here. And so now we are multiplying w with a matrix and y with a matrix. So now we set this expression to 0, bring this to the other side, and essentially divide it by x transposed x to get w. And this is how you write it. So this is on the left side, so you have to multiply the inverse to the left. So the least square solution is x transposed x, and the inverse of this times x transposed y. So and this is a very famous equation. I'm not sure if it has a name, but it will occur many times in the lecture. So get used to it. If you're not familiar with matrices and vectors or in general, I would encourage you to just use one of your favorite tools, MATLAB, Octave, or Python, or whatever, and just play around with this a little bit to get confident about what is going on. So the advantage is now that we don't have to do this step-by-step iteration process. Fixing this learning rate eta can be tedious, shouldn't be too large, shouldn't be too small. We can calculate everything without any learning rule, just in one step. So here's the one-dimensional case again. Here's the equation again. And the number of computations is proportional to on the order of the number of parameters to the power of 3. Now this is because if you look at this equation, it becomes, this matrix becomes, has a dimension of number of parameters times number of parameters, and inverting such a matrix takes a number of, the linear dimension MP to the power of 3. And then we also have to calculate this product here that takes n times MP square computations. And maybe a little bit surprisingly, if n is large, this is more expensive than the inversion. The inversion, as I said, if you have a nice tool like MATLAB or Octave, it's just a one line. You can almost type it in this way, in MATLAB, for example, and you get the inverse. So that's nice. We have a closed form solution. You don't have to do this nasty iterative optimization. And here are the rules I've used for the derivation. If I have a vector times a matrix, or matrix times a vector, and I want to take the derivative with respect to the vector, I get matrix transposed out. And if these would be just numbers, of course, that's the special case is completely obvious. If I have x transposed x, so the product of the vector with itself, but the vector is transposed, so this is a sum over the terms, then it's 2 times x, and if I have an expression like x transposed ax, then the derivative with respect to x is a plus a transposed x. One also finds slightly different conventions here, but they're all in themselves, they're consistent, and you would get exactly the same result. I like this version, but maybe you read some book or something and suddenly you find this version. They're both okay. So these are some of these equations you should find somewhere, or you have to derive yourself by hand, which is tedious. It's just better you find them in some nice reference text. One issue is the stability of the solution. If you have a little bit experience with linear algebra, then you always worry about when you invert something, because this matrix x transpose x might not be invertible, and so it can have 0 solutions, exactly 1 solution, or many solutions. So if we have much more data points than parameters, the least square solution in general is stable, which means small changes in the data lead to small changes in the parameter estimates. But the training error will typically be not 0, not some finite number. When we have fewer data points than parameters, then there are many solutions, so the solution is not unique, and they all produce 0 training error. So which one should we take of all these possible solutions? What one typically does is one selects the W's, so the weight vector, which minimize the sum over the square of the weight vectors. So if you have many, you can pick any one, and we take the one which is sort of the shortest, because if you think of this as a sort of the square of the length of this vector. So, and this is called regularization. So this makes the solution then unique. So before we had many solutions. When we decide to select the one which has the shortest length, we make the solution unique. And typically we always do it, not just in this case when we have few data points. As we will show in some examples, this is in general advantageous, in particular if you have many inputs, but also in general. So now we have to change the cost function. So here's our, and this is now called penalized least squares, or ridge regression, or weight decay. So we want to get some stability. So if it's changed one data point a little bit, the solution or the W shouldn't change dramatically. And in the case that we have many solutions, so many W's give you the same performance, we should pick the one which has the shortest length. So, and the way we're doing it, we are just adding another term to our cost function, which penalizes exactly this term. So this is the sum over all components of W squared. And we put some parameter in front, lambda, regularization parameter, which determines, if we have to do a compromise, how much we want to do this, how much we want to force the vector to have short length, and how much we want a good fit on the data. And so the nice thing, and very elegant thing, is that the solution, which we call now penalized, penalized least square solution, is is x transpose x plus lambda I, and I is the unit matrix we introduced last time. So so this is a diagonal matrix with ones of the appropriate dimension, and here's where the lambda occurs. You take the inverse of this and times the x transpose y. So from a computational point of view, no more cost. Basically no more cost, but maybe a more stable solution. And we get this by just also taking the derivative of this expression, which is 2 lambda w, and then you order these terms accordingly, the w terms and the rest, and then you get this solution very quickly. Yeah, and this is very powerful, and in machine learning you almost always do something like that. So you regularize your parameters. So if lambda is small, for example, and the parameters are well defined, it doesn't really change much. But the parameters which are not so well defined will become smaller. So we will see that in the example. We can also change the online learning rule to take care of this regularization. And so at each update, we go in the negative direction of the gradient, and we also subtract w divided by n times wj. So if you have a lot of, so this w divided by n is there, so the dividing by n is there, that we get exactly the same solution, but it also indicates if you do this online learning, this parameter here should be very small. It's typically very small because you would you would apply it at every data point. So you can also apply this weight decay in online learning, and that's why it's called weight decay, because if this w would not be driven by the error term, so for some reason this term is 0, then the w would just become smaller and smaller. And there's also some biological motivation why this makes sense. So also this idea, if you don't use it, you lose it. Which is also a principle in the brain. If you have a neuron which is not really used a lot, or some connections are not really used a lot, these connections sort of decay in time. So now let's apply what we have learned to a toy example. So I generated n equals 100 data points with m equals 3 inputs. And I did not use any bias, so W0 is always 0, and we don't show it. So the way I generated the data, x1 and x2 are highly correlated, so they're almost identical. And x3 is independent from x1 x2 and also from the output. So it's so these are typical situations. You see correlations between inputs. They're not independent. But then there are also some inputs which simply don't have anything to do with the output, but you don't know it. No. So I generated output data y as x1 plus epsilon. So and epsilon is independent noise with a standard deviation of 0.2. And the variance is then the square of that, 0.04. Thus the ground truth parameters, W true is 1, 0, 0. So only the first input is responsible for the output, and the others should not have any influence. Okay, so the true function is the way it is generated. Y is x1, no contribution from x2, no contribution from x3, plus some noise. And all variables, so all x's, all inputs, are normalized to 0 mean and variance of 1. So that's a typical pre-processing you're doing. You're subtracting the mean from every input, and then you divide it by the standard deviation, and then you get a variance or standard deviation of 1 for every input. So the true one is, as I said already, 1, 0, 0, and the W naught is not included. So first we do a one-dimensional analysis, or univariate or unidimensional analysis. So where we try to predict y for each input separately. So for x1, x2, x3 separately. In this case, I get for the w's, according to our formula, 0.99, 0.96, and minus 0.21 for the different parameters. So we have 3 models now because they're all independently modeled. The first one said the output should be the same as x1, which is correct. The second one says the output should be the same as x2, which is a good predictor, but of course it's not causal because x1 was the cause. And from the third input, I get, because of random disturbances and random effects, I get also a non-zero number here. And the parameters, if we apply the regression formula, is the sum over the product. So let's say we're interested in wj, so we take xij, multiply it by yi, and divide it by the number of data points, and that's the w. This is also called the Pearson correlation coefficient for later reference. So our estimate of that one, so these should be, I guess, estimates. They are identical. So the Pearson correlation is the same as the W in the estimate. So we can do a little bit deeper analysis, and we see that the expected value for W1, so if we would do a lot of experiments, is 1, and the standard deviation is 0.02. And of course this reflects the true causal dependency of y on x1, as I already discussed. The second one is in the expectation is also 1 and has the same standard deviation. And yes, so this of course is okay if you just say I want to predict y based on x2. Maybe I don't have access to x1. So as a prediction, this is absolutely okay. But of course, it doesn't reflect the true causal dependency. So the third one is closer to 0, but it has a lot of disturbance. So the standard deviation is 0.1. Considering that these are 0.02. So it's sort of correctly predicted that it shouldn't have an influence, but this is not really very well determined, because the value here is still quite considerable. So it looks like it has a negative influence. So now we do our least squares regression, where we use all the three inputs jointly. We can calculate this X transpose X matrix, which looks like this. So we have a strong diagonal, and then we also have these terms over here, which indicate the strong correlation between x1 and x2. And we can take the inverse, then we get this. And the third term, we have to multiply this by this. And this is simply n times the estimate of the Pearson correlation, 99, 97 minus 20. And if we do this formula and look what comes out, it's much, much more interesting, or closer to the truth. So the first one, W1, is correctly close to 1. This is the causal effect. W0 is much closer to 0. So this regression found out that it's not really W2, which is important, but W1. And the third one is also closer to 0. And if you look at the expected value, this should be the true parameter with sort of a larger standard deviation. The second one on expectation should be 0, which is a dramatic shift. It was 1 before, now the expectation would be 0. And the third one is an expectation should be 0 and has a smaller standard deviation. So in regression, the causal influence of x1 stands out much more clearly. And both the effect of the correlated input x2 is reduced, and also the noise influence is reduced. So if you are interested, I mean, of course, the prediction is typically not reduced. So if you have more inputs, that's okay. I mean, if you do multivariate analysis, but more importantly, and we will see an example in a second, in some applications, it is quite important that you get the true causal dependency. So in regression, an input, so a particular input only has to model what the other inputs could not model. So if x1 already takes care of producing a good model, x1, x2 and x3 are more irrelevant, and they sort of know that in some sense. Whereas in a one-dimensional analysis, I mean, every input has to do the job. x3 cannot do a good job because it's more or less uncorrelated, but the x2 can do a good job, and it does it. And as I said, as a prediction, it's absolutely okay. So if you just have access to x2 and you need to predict the output, then this is an absolutely okay model, but it doesn't reflect the causal dependencies. Okay, we can also look at penalized least squares. So with lambda equals 0.6, we get these results. And the interesting thing is, the causal one is even closer to 1. The x2, which is not causal, is smaller, and also the input of the effect of the noisy input is smaller. So if these inputs would be independent, which in our example they are not, in expectation, so on average, the least squares estimate would be reduced, or there's a shrinkage going on. That's called shrinkage estimate. And we divide the factors n is the number of data points, divided by n plus lambda. So we had n equals 100, lambda 0.6. So it's not really extremely changing the parameters. But there's a little bit more advanced analysis, which is interesting, but maybe something you don't have to completely understand on this round. So let's say we are transforming our input to another vector, z, by a matrix V transposed, such that the components of z are uncorrelated. So now we have really independent inputs, and the variance of the inputs is dj squared. So this is always possible. I don't discuss now how you do it. Essentially, you're using a principal component analysis, and we're just sort of rotating the data into a new coordinate system. And now we have everything is independent, but every input has a different sort of variance now, because we don't rescale the data. Then in this new coordinate system, when we apply a penalized regression, the shrinkage factor is now n divided by n plus lambda divided by dj squared. So not every parameter is reduced by the same percentage. The ones which are smaller are reduced. No, not the parameters which are smaller, but the ones where this dj square is smaller will be reduced more. No, because then lambda divided by this factor will be larger. And so this means that weights and dimensions of the small dj square are shrunk more. And as we will see later, we can also estimate the uncertainty in our estimate. So this variance and becomes sigma square. So this is the noise variance, the output noise, divided by n times dj square. So which means that weights are more uncertain when dj is small. So this shrinkage, or this application of penalized least squares, means that the uncertain weights get reduced more. And this probably explains the power of the penalized version, penalized least squares, in comparison to just least squares. So penalized least squares sort of has the effect that uncertain parameters or uncertain dimensions are reduced in the prediction. So what lambda should we take? We will analyze this in more depth later on, but to give you already an impression. So here we are increasing lambda. So if we, and this is the test set error. So we have a certain test set error with lambda equals 0. If we increase lambda, the performance increases because the parameter estimate gets better. And then if we do too much of it, then the performance gets worse again. So we should, as a general recipe, not pick any lambda, but we have to be a little bit careful what the right lambda is. But it's not, we don't have to be perfect. No? So if we have a little uncertainty in the way we pick lambda, it is absolutely okay. And then here's how the parameters change when we increase lambda. So W1 becomes smaller. W3 sort of is not much affected, and W2 even gets larger. Now this doesn't contradict what I said before, because W1 and W2 are not independent. But here at the location where lambda is best, no? We see exactly that W2 and W3 are close to 0, and W1 is a little bit reduced. Because this is the important point we're interested in, and we can select this point by looking at the test set error, picking the lambda, which seems to give the best test set error. Yeah, this is how the W's evolve in time with the number of data. Sorry, not in time, but with the number of data points. So when we have a very small number of data points, because of this penalized penalty term, the weights will be closer to 0, and then when we have more data, they assume their values. And the average test set error also goes down when you increase the number of training data points. This is the example for least squares. So looks sort of similar, except that the parameters are more noisy in the beginning, more unstable. Eventually the parameter estimates with increasing n become very similar, but with a very small number of n, we get a lot of uncertainty. Whereas this uncertainty in the parallelized version is not really there. Okay. So in healthcare, this can be very important. So let's assume the same data, and let's assume that X2 is a treatment, like a particular medication, and Y is the output. So the patient after the treatment is healthy. That means Y equals 1. Otherwise, Y equals 0. So if I do a one-dimensional analysis, I would see a strong positive influence of X2 on Y. So almost in our experiment, it means the Pearson correlation was 1, right? Very close to 1. So in this case, I would conclude that the treatment really works. Great medication. But then if I include X1 in the analysis, and in this case in the healthcare it would be called a confounder, then of course X1 gets this really high weight of 1 and X2 gets an influence of close to 0. And I would conclude, no, it was not an effect of the medication or of the treatment, it was an effect of X1, which was sort of influencing the reason to get the medication and also influenced the outcome. So, and this is a very central issue in healthcare, that if you don't include all the important factors in your predictive model and you just do a one-on-one analysis, that can be quite misleading. In particular, if you have an input like X1 which influences the output and also influences the medication. So, and typical confounders are female, male, or age group. So sometimes the medication works in a certain age group and doesn't work in another age group. Or as a general rule, if you're looking at data which was not produced in a clinical study, but just by observing what doctors are doing, anything the doctor considers in making the decision on the patient, so giving the medication or not giving the medication, should be included also in your model. So that's a general rule. So if you have a blind doctor which doesn't look at the patient at all and just gives randomly the medication out, that might not be a good doctor, but it gives you the easiest analysis on the effectiveness of the drug. But if a doctor looks at patient properties when the doctor makes it, and this is the case in a clinical study. You should randomly assign the medication to patients to get. That's why we are doing these clinical studies, because then there is no confounding factor because it's a random decision. But if your decision, the doctor, if you observe data and the decision of the doctor was influenced by some of the patient properties or other things, all these things should be inputs to your model. That's sort of the general rule. And here's again the difference between the models. So here's the true model. So X1 was the real cause, and X1 sort of influenced. So in this example, it would influence the medication, or if you give the medication or not. and x1 is the cause of the outcome if somebody gets healthy or not. So that's the ground truth. If you do the one-dimensional analysis, you see the true dependency from x1, the true dependency from x1 on y. You also see a dependency of x2 on y, but this is not causal. It's just a prediction model. And you see that the influence of x3 can also be not quite eliminated. But if you have a well-tuned penalized least squares model, you discover that x1 is the true cause, x2 the medication has no influence, and x3 also likely doesn't have any influence. So with this penalized, so first of all, the big step is from univariate to multivariate. Multidimensional, one-dimensional to multidimensional, and so that's a big thing, and then a further improvement by using a penalized least squares approach. So now the study would say, no, the medication doesn't have any influence. Of course, this is a very extreme case, but this is not unimportant. This is also the reason why you sometimes see all these strange reports about things causing things, which might be completely irrational, and maybe it is irrational, and often it is just the result of a one-dimensional analysis where one should have done a multi-dimensional analysis. So in the old days when people were still smoking a lot, and why could have been, sort of the other case, why would be somebody gets breast cancer, and x2 was smoking, so there was a clear correlation or dependency. But of course, then people argued that, oh no, it's not smoking to breast cancer, it's some genetic factor, and this genetic factor made you want to smoke and made you more likely to get breast cancer or some lung cancer, not breast cancer, sorry, lung cancer, of course. And if you stop smoking, that has no effect. Of course, this model is not correct in this case. Smoking is a cause for lung cancer, but of course there are some confounding factors, and the result is influenced by other factors. For example, if you work in a very unhealthy environment, you might have a low-paying job, you might be in a population where people tend to smoke, and this unhealthy environment also maybe gives you lung cancer. So it's not quite unreasonable to assume that there are confounding factors in this problem. But yeah, studies have shown that there is a true dependency. But it's still, occasionally it's still analyzed, and people find some more interesting insights into this problem. So that's also why, making decisive or really certain medical statements about dependencies and effectiveness of drugs are so difficult to get. Even if you are a very careful statistical expert, you might still run into these problems. So remember what Pearson said. Now, he was really happy about the Pearson correlation factor. It's named after him, because it seems to be more something related to science. The correlation does not change if I measure other things. It's a thing between two things, so x1 and y, or x2 and y, or x3 and y. But if I add more, the Pearson correlation doesn't change. So he claimed it was, or he was hoping that this was more a scientific measure. Whereas the regression, of course, depends on what other factors you're also considering. But as we discussed, it can be quite important if you want to discover true causal dependencies. And of course, the analysis of causality on observed data is a big topic on its own. But this issue with confounding factors is sort of absolutely central to this analysis. So if you are interested in particular in prediction accuracy, but maybe also causality, you can maybe you're tempted to add more and more inputs. And it's okay if you use regularization. Huh? So in advertisement, so placement of advertisements and advertisements bidding, they use hundreds or thousands of features to determine user features or behaviors and so on. So there are a lot of inputs, and if you use regularization, your chance is quite good that this will still work, because the unimportant inputs the influence of the unimportant inputs will be reduced by the regularizations. And it's particularly important when the number of data points is approximately the same as the number of parameters, or when it's even worse, you have smaller number of parameters, then you have degrees of freedom. And in particular, when we will discuss about kernel approaches, this is quite dramatic, because the number of parameters can be infinite. Of course, you don't have an infinite number of training data. So there, the regularization really saves you and gives you good results, even in that case. But sometimes you don't want to do this. You don't want to just add a lot of inputs and be just happy about good predictive performance. Sometimes you want to have interpretable results. So you want to find, in some sense, the true inputs, which is a little bit difficult, as we discussed. Or you want to have a small model for computational reasons or other reasons. And there are two standard strategies. One is forward selection. You start with an empty model, and then you add at each step the input to your model, which decreases your test set error most, or training error. Both are possible. And then at some point you stop. So it's sort of a greedy approach, step by step. It doesn't guarantee that you get the best subset of inputs, but it's a very practical strategy. Or you do the other direction, you start with a full model with all the inputs, and then in each step you try out and you remove the one which seems to decrease or increase the error the least. So both strategies are legal, and you can do a mixture of both, or some more fancy needling approach, or genetic approach. There are many different ways. It's not as important as you might think, except when you're interested in interpretability. But it's also a little bit dangerous. You might also kick out important inputs in this procedure. Yeah, here's another example where, so this is from Hasty's book, the data mining book. An example with 8 inputs and 97 data points, and the output was to predict a prostate specific antigen. And he used 10 times cross-validation test error. And if you do least squares, you get an error of 0.58. If you do a selection for the best subset of inputs, so you're removing some of the inputs which are useless, and you end up with 3 inputs, not 8, then the performance gets slightly better if you do a good job. But if you do a penalized regression, this in statistics also called rich regression, the improvement in performance is even more dramatic with all the 8 inputs. So here you would use all the 8 inputs. So this shows you the power of penalized least squares, and it also shows you that if you're only interested in performance improvement, maybe you don't have to do fancy input selection. Yeah, here are some examples where high-dimensional linear systems are used. One is the ranking in search engines, so the estimate of the relevance of a web page to a query, or in advertisement placement, where to put which ad for a given user, for example. But least squares regression and also penalized least squares regression is sort of one of the most important tools in statistics. So if you study statistics or attend some lectures in statistics, this is one of their most important tools. In machine learning, we typically are using non-linear models, so not the linear models here, but even there, as I discussed before, the last layer of processing is often a linear system, either a linear classifier or linear regression system. So it's also a very important basic building block in machine learning.